Assalamu alaikum everyone. I hope that all of you are safe and sound. I welcome you all to the fourth lecture on analog and digital electronic circuits, in which we will study different biasing schemes for the BJT amplifiers. In lecture 3, I have already talked about the need for biasing of the BJT amplifiers. So after quickly reviewing the objectives of the biasing schemes, I will discuss various biasing networks in which I will present mathematical expressions for the bias points of the biasing networks, as well as the relations which can be used to design the respective biasing networks. So as we all know by now that BJT is a highly nonlinear device because its output collector current has an exponential dependence on the input base emitter voltage. To ensure that the BJT amplifier operates in the linear active region of the voltage transfer characteristics, appropriate DC voltages must be applied at its input. So the circuits which generate and apply these DC voltages to ensure linear operation of the resulting amplifier, these circuits are called DC biasing circuits or DC biasing schemes or DC biasing networks. So as we saw in lecture 3, the output collector current as well as the output collector emitter voltage of a BJT amplifier, they depend on the transistor parameters. For example, the collector current is given by the scale current of the transistor, which is a strong function of the temperature. So by varying the temperature, the scale current varies, which in turn varies the bias point of the amplifier. In addition, there are manufacturing induced variations in the transistor parameters, which means that given any two transistors, their parameters can never have exactly the same values. There will always be some slight variations in their parameters, even if the transistors they come from the same manufacturing process. They will always have slight differences in their parameter values. So these variations in the parameters, either temperature or manufacturing induced, they change the bias point of the amplifiers. So in addition to biasing the amplifier, an important objective of the design of a biasing circuit is to ensure the stability of the resulting bias point against such parameter variation. So in this regard, we will study the biasing scheme by taking into account the variations in the beta parameter of the transistors. So in other words, we will gauge the performance of the DC biasing networks by analyzing the stability of the resulting bias point against variations in the beta of the transistors. So the first biasing scheme that we will study is called the biasing using fixed VBE. It's a very simple network as is shown here. So the base emitter voltage is fixed by this DC source labeled VBE, and this VBE produces output current IC and the output voltage VCE, which are given by these simple relations. So the collector current is exponentially related to the base emitter voltage, and the output collector to emitter voltage is given by VCC minus ICRC. ICRC is the drop across RC. This equation for the collector emitter voltage can be inverted to get the equation for the collector resistance RC. So these two equations, they represent the bias point of the circuit, and given the bias point, we can use this equation to design this biasing scheme. That is, we can find the resistance required to set up the bias point given by IC VCE at the output. So as we can see that VBE is fixed, which makes the collector current directly proportional to the scale current. And since the scale current is a strong function of the temperature, so the resulting bias point becomes dependent on the temperature, and hence is highly unstable during the operation of the amplifier, because the transistor will get will get hotter, its temperature will rise, which will vary IS, and that in turn will vary IC and VCE. So the bias point is highly unstable in this case. And furthermore, the bias point is also subject to manufacturing variations because IS can vary across transistors, even if they come from the same manufacturing process. So the next scheme is called fixed bias. It is also called biasing with fixed IB because if you look at this circuit, then uh, this end of the base resistance RB is at a fixed potential of VCC, at a fixed voltage of VCC with respect to ground, and the base emitter voltage is also uh, can be taken to be constant because we know that a base emitter junction is forward biased, and during forward biased operation, the forward voltage does not vary much. So the base is also at an almost fixed voltage. So the voltage across RB is constant, which generates constant base current. That is why it is called biasing with fixed IB. So by writing the voltage equations around this loop, we can find the base current as VCC minus VBE over RB. And then we can multiply the base current with beta to get the collector current. So collector current is given by this equation. Similarly, the output collector emitter voltage is given by writing an equation for the voltage around this loop. So VCE is given by VCC minus ICRC. We can invert this equation to get the expression for RC given the bias point VCE and IC. And similarly, we can invert this equation to find an expression for RB given the bias point given IC and VBE, where VBE is given by the collector current and the scale current. So again, in this configuration, the collector current is directly proportional to the beta of the transistor. So beta is a temperature dependent parameter. So as the temperature varies, beta will vary, which will vary IC and eventually VCE. So again, this is uh, although a simple biasing scheme, but it results in a bias point which is unstable against beta variation. The third biasing network is called the emitter feedback bias. It looks similar to the fixed bias network. The only difference is that we have this emitter resistance now, and this emitter resistance, as I will show in a minute, helps to maintain the stability of the bias point against beta variation. So we can write the KVL around the voltage equations around this loop. We can write the KVL around this loop, which is given by this equation. So VCC equals the drop across RB plus the drop across VBE plus the drop across RE. And then we can relate IB and IE to IC through beta and invert this equation to find the expression for IC, the output collector current. And similarly, we can write voltage equation around this loop to get VCE. So VCE is given by VCC minus the drop across RC minus the drop across RE. So again, IE can be related to IC through beta because IE is IC over alpha and alpha is beta over beta plus 1. So we get this expression for the output collector commutator voltage. So this gives us the bias point of this circuit given RB, RC, and RE. On the other hand, given the bias point, IC and VCE, we can find the three resistors using these relations. So this equation here can be this equation here, in which we can represent IERE as the voltage drop across RE. This equation can be inverted to get an expression for RC. And similarly, RE can be found by dividing VRE with IE. And again, we can invert this equation by replacing IERE with VRE to find an expression for RB. So given the bias point IC, VCE, and VRE, we can find we can design the network using these resistance values. So, like I said, the difference between fixed bias and emitter feedback bias is the emitter resistance RE, which provides negative feedback to maintain the stability of the collector current. For example, assume that IC increases due to some variation in beta, which will increase IE because IE is IC over alpha. So IE will increase, which will increase VRE because RE is fixed. So when current through RE increases, VRE will increase, which will in turn increase VB because VB equals VBE plus VRE. So VB will increase. When VB increases, IB will decrease according to this relation, because we can write the equation for IB as VCC minus VB over RB. So when VB increases, IB decreases. When IB decreases, then IC, because it's related to IB through beta, IC will decrease. So the increase in IC will be countered by the increase in voltage VRE, which will eventually increase VB and decrease IB and decrease IC. So this emitter resistance, which provides a negative feedback, helps in maintaining the stability of the bias point, and in this respect, it is also called emitter degeneration resistance. Also notice that typically VRE is specified as 10 to 20% of the supply voltage. So if we look at this equation here, then IC has a direct dependence on beta. So if we could somehow reduce RB and make it much smaller, much small compared to this term, beta plus 1 RE, then we can approximate the denominator with beta plus 1 RE. And since beta is a large, the parameter beta has typically large values of the order of 100, beta over beta plus 1 is almost 1, very close to 1. So if we are able to approximate the denominator with beta plus 1 RE, then we can make IC approximately independent of beta. But unfortunately, in this game, that cannot happen because, like I said, VRE is typically mentioned to be 10 to 20% of VCC, which means that the designer does not have any control over RB. It is given by VRE. So we cannot reduce RB to arbitrarily small values. And hence we cannot make it arbitrarily smaller compared to this term, and eventually we cannot obtain beta independency in this case. IC cannot be made beta independent because RB cannot be made arbitrarily small because in turn it is given by VRE, which, like I said, is typically specified to be 10 to 20% of VCC. So the next scheme is called collective feedback bias, and as the name suggests, in this scheme, the negative feedback is provided by the collector resistance, RC. So by writing the voltage equation around this loop, we can write VCC as the sum of the current through RC times RC plus IB, RB plus VBE. The current flowing through, if we designate the current, this branch current as the collector current, this is the base current, then the current flowing through RC is IC plus IB. We get this equation. We can invert this equation by representing IB in terms of IC through beta and get the output collector current given by this expression. Similarly, we can write a voltage equation around the output loop and get an equation for the output voltage of the circuit. So given the circuit, we can find the bias point using this and this relation. Conversely, given the bias point IC and VCE, we can design the circuit using these equations. So RC is obtained by inverting this expression here, and RB is obtained by finding the voltage at this node and at this node, and then subtracting the two voltages and then dividing by IB, which is IC over beta. So the voltage at this node, which is the collector node, is VCE, and the voltage at this node, which is the base node, is VBE. So RB is given by VCE minus VBE over IB, which is represented as IC over beta. So given IC and VCE, we can design the circuit using these relations. So like I said, the collector resistance provides negative feedback and helps in maintaining the stability of the bias point. Again, we can see this by assuming that IC is increased due to some variation in beta. Then this increase in IC will increase the current through RC. So the current through RC will increase, and since VCE is given by this relation, so increase in RC decreases VCE, which will decrease IB according to this relation. So this expression is obtained by inverting this expression. So this current is IB. So IB decreases when VCE decreases. So when IB decreases, IC will decrease because IC is related to IB through beta. So in this way, the increase in IC is countered, and the negative feedback provided by this RC helps in maintaining such a negative feedback provided by RC helps in maintaining a stable bias point at the output. But in this case, the stability of the bias point is better than it was in the case of emitter feedback biasing. Because if you remember, then IC was given by a similar expression for emitter feedback bias. The only difference is that in the denominator, we have, instead of RE, we have RC. And typically, RC has a large value than RE. Also, the base resistance RB in this case, it is, so let's go to the slide. I have these equations over there. So like I said, typically RC is larger than RE. And then for the same base current, the base resistance in collector feedback bias, which is given by this expression. This is the same expression as shown earlier. This base resistance is smaller than the base resistance in the emitter feedback bias, which is given by this expression. Why? Because as mentioned earlier, VRE here is set to about 10 to 20% of VCC, which means that this term VCC minus VRE is about 80 to 90% of VCC. Whereas VCE itself is about 50% of VCC. We discussed this in the last lecture that in order to bias the circuit in the middle of the linear active region of the VTC, voltage transfer characteristics, to obtain maximum head and tail swing, we need to have VCE about 50% of the VCC. So when VCE is about 50% of the VCC, then the bias point is right in the middle of the linear active region of the voltage transfer characteristic. So typically VCE is about 50% of VCC, and this term is about 80 to 90% of VCC. So the denominator is clearly larger in this case than in this case, which means that this RB in the collector feedback bias is smaller than this RB in the emitter feedback bias, which in turn means that RB in the collector feedback bias is much smaller than beta plus 1 RC than it is in emitter feedback bias compared to beta plus 1 RE. So what I'm trying to say is that this denominator is better approximated by beta plus 1 RC than this denominator uh, with beta plus 1 RE. So the approximation here of this denominator with beta plus 1 RE is a loose approximation, but the approximation of the denominator here with beta plus 1 RC is a better approximation, because RB, not only RB in this case is smaller than before, RC is generally larger than RE. So beta plus 1 RC has larger magnitude in this case compared to RB, and then beta plus 1 RE compared to RB in case of emitter feedback bias. So, so if this is a better approximation, if the denominator is better approximated by beta plus 1 RC, then we get better beta cancellation. So this, in this case, IC has a weaker dependence on beta than in case of emitter feedback bias, and hence IC is more stable against beta variations in the collector feedback bias compared to the emitter feedback bias. So this better helps to nullify the dependence of IC on beta. The next biasing scheme is called collector emitter feedback bias, and again, as the name suggests, this is a combination of collector and emitter feedback bias, in which we have the collector resistance and the emitter resistance both providing the negative feedback. So writing the voltage equation around this loop, we can find the collector current, which is given by this equation, and similarly writing an equation around this loop, we can find the output collector to emitter voltage, which is given by this equation. So given the circuit, we can find the bias point using these set of equations, this and this equation. On the other hand, given the bias point IC and VCE, we can design the circuit using these relations. So RC is again found by inverting this expression, in which this term is replaced by VRE, because this beta plus 1 over beta into IC is emitter current. At times RE gives us the voltage across RE, and then we can invert it to find RC. RE again is given by the voltage across the emitter resistance RE divided by the emitter current, and RB is found again by finding the voltage at this node, finding the voltage in this node, subtracting the two voltages, and dividing by IB, which is given by IC over beta. So the voltage at this node, which is the collector node, so the voltage at collector with respect to ground is VCE plus VRE. Similarly, voltage at base with respect to ground is VBE plus VRE. So when I'll take the difference, VRE will get cancelled out, and I'll be left with VCE minus VBE. So RB is given by this simplified expression. So at first sight, the collector emitter feedback bias appears or may appear to be more stable than the collector feedback bias against beta variations, because previously we had in the denominator beta plus 1 RC, but now we have beta plus 1 RC plus RE. So one may think that since this is the sum of two resistances, this term is now even larger than RB. And one may think that uh, this denominator may be approximated by this term, and this new approximation is an even better approximation. One may be tricked into thinking that, but that is not the case here, because if you look at RC and RE, and if you find RC plus RE through these relations, then the denominator is the same, and in the numerator, when you add the two, VRE will get cancelled out. So RC plus RE is actually given by VCC minus VCE over this current, which is actually the same expression we use to find RC of the collector feedback bias, VCC minus VCE over this current. So the resistance RC in collector feedback bias is actually equal to the resistance RC plus RE in collector emitter feedback bias. So this resistance here in the collector feedback bias is the same as RC in the, this resistance here in the collector emitter feedback bias is exactly equal to the resistance in the collector feedback bias. So this sum in the collector emitter feedback biasing scheme is equal to RC in the collector feedback bias. And RB is the same for both schemes. So RB here is VCE minus VBE over IB, and RB for the collector feedback bias is VCE minus VBE over IB. So for the same bias point, RB for the two schemes, collector emitter feedback bias and collector feedback bias, they are the same. And RC for the collector feedback bias is equal to RC plus RE of the collector emitter feedback bias. So this denominator is actually the same for collector emitter feedback bias and the collector feedback bias. So this collector emitter feedback bias does not offer any additional stability of the bias point against variations in the beta of the transistor. So why do we connect RE? There are advantages of connecting RE of this emitter degeneration resistance, which will be discussed when we discuss the design of the voltage amplifiers. So the next scheme, which is perhaps the most commonly used biasing scheme, and is called the voltage divider biasing scheme, is motivated by the idea of obtaining a collector current which is independent of beta. So we would like to obtain a collector current which is given by an expression like this, in which beta and beta plus 1, they almost cancel each other, and IC becomes beta independent. So this collector current is given by this biasing circuit. So if you have a biasing circuit like this, you can see that the output collector current is then given by this expression. This expression is obtained by writing a KVL around this loop, around the input loop. So VB equals VBE plus IERE. So IE can be written in terms of IB or IC to beta, and we'll get this relation. So the exact physical circuit for the voltage divider bias is given by this diagram. So this is the circuit that we would want to achieve. This is the biasing circuit that we would want to get in order to obtain beta independent bias point. And this is what we design. This is what we use to bias the BJT with IC and VCE. So if we look at the circuit of voltage divider bias on the base side, then we can replace this part of the circuit through its Thevenin equivalent, where V Thevenin is the open circuit voltage between these terminals, and R Thevenin is the resistance looking into these terminals. So we want to find an equivalent circuit looking into these two terminals, into the base and the reference. So from Thevenin's theorem, we know that V Thevenin is given by the voltage division of VCC. So open circuit voltage across R2 is given by this fraction of VCC. And when we want to find if, the resistance looking into this port, which consists of these two terminals, this terminal and the ground, we'll have to short circuit VCC, which brings R1 in parallel with R2. So R7N is then given by the parallel combination of R1, R2. So this is the Thevenin's equivalent circuit corresponding to this portion of the voltage divided biasing network. So the resulting equivalent, Thevenin's equivalent circuit for the voltage divided biasing network is given by this diagram. So you can see that it is pretty close to the one that we desired. The only difference is that we have a Thevenin resistance. So it's not exactly what we desired, but it's the next best thing. So I will discuss the advantage of this R7 in a minute. So again, if we write the voltage equation around this loop, the KVL around the input loop, we can very easily see that IC, the collector current, is given by this expression. And similarly, writing a KVL around the output loop will give us VCE through this expression. So given the circuit, we can find the bias point. Or given the bias point, we can find the circuit resistance, RC and RE. So we can invert this relation for VCE, in which IC times beta plus 1 over beta times RE is the voltage across RE. So inverting this relation, we can find RC. And similarly, as before, RE is given by the ratio of VRE to IE, which is given by this expression. So this circuit is most commonly used because it has much better bias point stability compared to the other biasing schemes. Why? Because previously we did not have any control over RB. Remember, we used to have RB here, and it used to be set by VRE. So we didn't have any control over RB, but now there is no constraint over R7. R7 is fully under designer's control. So we can make it as small as we want compared to this term. So a typical choice is to set R7 to any value less than 1/10 of beta plus 1 RE. So when this term is 10 times smaller than this term, then we can replace the denominator with an approximation. We can approximate the denominator with beta plus 1 RE, and then beta and beta plus 1 can be assumed to be almost equal to each other. This ratio beta over beta plus 1 is almost can almost be assumed to be 1, which will result in IC getting independent of beta. So that is why appropriately selecting this Thevenin resistance reduces the dependence of the output collector current on beta, and hence renders the output bias point stable against beta variations. So it still remains to find out R1 and R2, because this is an equivalent circuit. This is not the physical circuit. This is an equivalent circuit. Physical circuit is given by this diagram here on the left. So in this diagram, we still need to find out R1 and R2. So once we have chosen an R7, we can find VThevenin as well, because like I said, VRE is typically specified to be 10 to 20% of VCC. And VBE is given by the output collector current. So given the bias point, we know VBE, we know the specified VRE, we have chosen our Thevenin, so we can find VThevenin as IB times R Thevenin plus VBE plus VRE, where IB can again be found from IC. So VThevenin can be found. So what I'm trying to say is that we know VThevenin, we have selected some R Thevenin, we know the supply voltage as well. So we can solve these two equations to find R1 and R2. and R1 and R2 are then eventually given by these expressions in terms of VCC, R7N, and V7N. So given the bias point and the specified VRE, we can use these two equations along with these two equations to design the voltage divider batching network shown here in this diagram. So at this point in time, I would like to give you an exercise to make sure that you absorb all of this material, especially the equations. And in order to better absorb the equations, I want you to go through this exercise yourself, in which in the first part, you should design all of the biasing circuits that we have discussed so far for the bias point given by IC and VCE. Assuming that the supply voltage is 15 volts, VRE is 10% of VCC, and beta of the transistor is 100. So you just need to plug in these numbers into the equations already shown in the previous slides to find the respective collector base and emitter resistance. Once you have designed the biasing networks, in the second part, I want you to assume that data is now increased from 100 to 200. So new beta is 200. So using the biasing circuits that you have designed in part 1, I want you to find the new bias points. I want you to find IC and VCE for all of the biasing schemes. And then I want you to identify which biasing scheme of the ones we have studied is the most stable biasing scheme. Obviously, the most stable biasing scheme will have the new bias point very close to the old bias point. And the least stable biasing scheme will be the one in which the new bias point is farther away from the old bias point. So please do this exercise yourself. It is very important for you to solve these circuits and let the mathematics flow through your hand in order to get better familiarity with these equations. So the next biasing scheme is actually a variant on the voltage divider biasing scheme. This one uses two power supplies, VCC and minus VEE. For a physical connection of VCC and minus VEE with the circuit, I would refer you to the first lecture in which I showed the exact physical circuit by connecting VCC with the negative terminal of the VCC with the positive terminal of VEE, and then using that common terminal as the ground node. So I have shown this physical connection in the first lecture when I biased the black box of the amplifier with dual supply. So in this network, we can again solve for the circuit on the base side of the network and find its Thevenin equivalent. And the resulting Thevenin equivalent voltage divider biasing network using dual supply is shown on the right here. So as you can see, the only difference is that instead of ground, we have minus VEE. So the new Thevenin voltage will have, instead of VCC, it will have VCC plus VEE, because now the total voltage instead of VCC is VCC minus of minus VEE. So the total voltage is VCC plus VEE. And the Thevenin resistance will remain the same. So the expressions for the bias points as well as the expressions for the resistances given the bias points, they will almost be the same. The only difference will be that instead of VCC, you will have VCC plus VEE everywhere, as you can see. So I want you guys to derive these equations yourself. It's best if you derive these equations yourself in order to get a better idea. This circuit here shows the dual supply voltage divider biasing network. for the PNP amplifiers. So all of the biasing schemes that we have discussed, they can be applied to PNP amplifiers as well. So I am going to apply this dual supply voltage divider network to PNP, only this biasing scheme to PNP. You can apply the other biasing schemes yourself. All you have to do is, because you understand that PNP transistor has operating voltages which are exactly opposite to that of an NPN transistor, and its branch currents are given in exactly the opposite direction to the branch currents of the NPN transistor. So for an NPN transistor, if the collector current enters the collector terminal, for a PNP transistor, the collector current will leave the collector terminal. For an NPN transistor, if the emitter current leaves the emitter terminal out of the circuit, then for a PNP, it will enter from the external circuit into the emitter terminal. The base current will go out of the base terminal, because for the NPN, it went into the base terminal. So the current directions as well as the voltage polarities are reversed. So previously we used to have VBE, now we will have VEB. And instead of VCE, we will have VEC. Everything else will remain the same. So the positive supply is now connected to the emitter terminal, so it's called VEE, and the negative supply is connected to the collector terminal, so it is now represented by minus VCC. So the Thevenin equivalent circuit will again be given by a similar diagram, in which V Thevenin will again be given by the total voltage, which is VEE plus VCC, and the Thevenin resistance will remain the same because we haven't changed this part of the circuit. So it will be given by the parallel combination of R1 and R2. And the relations, the equations for the bias point as well as the resistor values, they will be given by similar expressions. The only difference is that instead of VBE, you will have VED, and instead of VCE, you will have VEC everywhere. So again, in order to get a better idea, I would highly recommend that you guys derive these equations yourself to get a better idea of what is going on in the circuit. So we can also obtain a single supply voltage divider biasing network for the PNP amplifier by setting VCC to 0. This will give us an equivalent circuit, which will have branch currents and node voltages given in opposite directions and opposite polarities respectively when compared to the single supply voltage divider biasing network for an NPN amplifier. So the performance of the biasing scheme can be quantitatively gauged using the beta stability factor, which we denote by S and define as the rate of change of the collector current with respect to beta. So you guys have now the equations for the collector current for all the biasing schemes that we have discussed. So I would highly recommend that you find the stability factors for all of the biasing schemes by simply differentiating the collector current with respect to beta. I will find the stability factor for only the voltage divider biasing network, for which the collector current is given by this expression. So differentiating this expression with respect to beta gives us this result, in which the denominator, because of the square, this denominator is a relatively larger term, which results in a smaller value for the beta stability factor, which is indicative of the fact that voltage divider biasing networks, they have better stability of the bias point against beta variation. So this brings us to the end of this lecture. Thank you very much for your time. I will see you in the next class. Take care.